Hello, this is Professor Kevin Mark. This is the Prelab lecture for Lab 1, Density of Solids and Liquids. Many more lectures to come after this. So let's just get started. Lab 1. The two topics I'm going to focus on is significant figures and density. So with significant figures and measured numbers, we have both exact values, which we're used to dealing with. For instance, a dozen is 12 eggs, $1 is 100 cents, 1 inch is 2.54 centimeters. Those are exact conversions. 1 foot is 12 inches. But the majority of the time, what you'll be doing in the lab is measuring inexact numbers, and that's because of measurements that you take. Every instrument has a particular uncertainty, and also person by person there's some kind of uncertainty when you measure something. So for instance, if I gave you a pencil and I asked each one of you to measure the mass of that pencil, you'll probably all give me different numbers, slightly different numbers, and that's because of the machine that you use or the way that you take the measurement, or the way that you read the numbers as well. So in the lab, and for most of the labs, you have to pay attention to significant figures. So if I asked you outside, what is the temperature? One device might say 75 Fahrenheit, one might say 75.4, one might be very precise and say 75.43388, etc. So when we talk about significant figures, hopefully maybe we've touched upon this in the lecture. This here, if you get a measurement of 75 degrees Fahrenheit, that's 2 significant figures. Here we have 3 significant figures for the next one, and we have 4 significant figures for the final number here. What are some rules for significant figures? Well, there's about 5 or 6 rules. The first one, all non-zero digits are significant, so all of these are non-zero, so they're all significant. There are 4 significant figures or digits. We can say sig figs. Anytime there's a 0 in between 2 non-zeros, that's considered significant. So in this case, we have 1, 2, 3, 4 significant figures. Another rule here, any zeros at the beginning of a number are not significant. So here, the 2 zeros in the beginning are non-significant. So in total, there'll be 2 significant figures. If the value was 0.0350, that would be considered 3 significant figures. So in this case, we have 4 significant figures because this 0 is in between 2 non-zeros. So again, 4 significant figures, 1, 2, 3, 4. The value before here is not significant. Any zeros that are after the decimal place are considered significant. So here we have 3.00, that's 2 significant figures. If I were to write 3.000, that would be 4 sig figs. 3.010, that would also be 4 sig figs. So this comes with practice to figure out how many significant figures to do examples. Here's just the summary. Rule 0 to 3b. One thing that I think differs a little bit from your textbook, if you have the number 320, this signifies 2 significant figures. If you include 2 significant figures. If you include the decimal point here in your measurement, so if you wrote 320 dot, that would be 3 significant figures. And another way to write this is through the scientific notation, where you write 3.20 times 10 to the power of 2. this signifies 3 significant figures, because in your coefficients for the significant figures, you got 3.20, so that would be 3 significant figures. If you had written 3.2 times 10 to the 2, that would be considered 2 significant figures. So let's just try to put these examples together, hopefully straightforward. The first example, how many significant figures are there? There are 3, 1, 2, 3. If you wanted to write this in scientific notation, it would be 3.51 times 10 to the power of 1, 2, 3, 4 to the negative 4. For question B, how many significant figures? It's 1 significant figure here. The zeros after are not considered significant. And for the next one, there are 5 significant figures. 1, 2, 3, 4, 5. And these trailing zeros afterwards are not significant. So 5 significant figures for C. Hopefully you know beforehand if you're rounding up or you're rounding down. So in this case, we have 6.43. And if you wanted the answer in 2 significant figures, you look at the digit on the far right and notice that it's 4 or below. So you would keep it at 6.4. Conversely, if there's something 5 or greater, you would round up. So in this case, if it was to write 2 significant figures, to 2 decimal places, so 5.98, would that stay as an 8, or would you round up to 9? You round up to 9 because this value here is 5 or greater. So the answer would be 5.99. There are some rules when you multiply and divide. So we're building on the significant figure rule. So if you know those significant figure rules, you can build on that by multiplying and dividing. So the rule is when you multiply or divide, you have to take into account the least significant figures. Meaning that, look at this question here. If you look there in the question, there's 3 significant figures here in the first number. 3.21, that's 3 significant figures. The next one has 4 significant figures. And the next one has 5 significant figures, 10.401. So according to our rule, you take the one with the lowest significant figures. So 3.21 has the least significant figures. And then therefore your answer has to have 3 significant figures. So when you multiply all this out, you get 167.503.63. You want the least significant figures, so you need 3 because this question here has the least is 3. Therefore your answer needs 3, so the answer would be 168 centimeters cubed. So again, everything should have a number and a unit. It's a little bit different for adding and subtracting. The rule is that the answer should have the least amount of decimal places, not least amount of significant figures, but least amount of decimal places. So in this example here, we have 98.4, which is 1 decimal place. The following number, 8.125, has 3 decimal places. And the following number has 2 decimal places. So when you add up all these numbers, you get 107.405. However, if we look at the question, the one with the least decimal places here, 98.4, is 1 decimal place. Therefore, your answer should have 1 decimal place as well. So the answer will be 107.4. So we try some examples. You can pause the video now and try it on your own using the significant rules we just learned. The answer is here on the bottom right, but I'll go step by step. So the first one, 3 times 9 is 27. Yes, but the question has one significant figure in each of the numbers. Therefore, your answer needs one significant figure. So you have to write this as 30 because you're rounding up. So now this answer has one significant figure. When you wrote 27, that's two significant figures. So you don't need to tell your friends or family that 3 times 9 is 30. That can stay within our chemistry class, that 3 times 9 is 30 due to our significant figure rules. The next one, B, 9.63 divided by 14.7. Well, in both cases, you have 3 significant figures, so your answer needs 3 significant figures. When you do this calculation, you get 0.655, I believe, 1. However, you want the answer in 3 significant figures, so you remove the 1 because it's less than 5, so we keep the 0.655. For question C, again, it's the different rules, the least amount of decimals. In C, you have 1 decimal place, and you have 3 decimal places, so your answer needs 1 decimal place, so your answer should be 728.7. When you do the calculation, it comes out to 728.68. You round up to 728.7. The following rule, you use the PEMDAS, so you use the parentheses, you calculate the parentheses first. When you do that, you do the 313.44 minus 209.1. So this comes out to 104.3. So that's the rule. For the minus subtraction, you have the least decimal places, and then you multiply this number by 8.2234. So looking at these two numbers, when you multiply, the rule is you need the least amount of significant figures when you multiply or divide. So your answer needs 4 significant figures. And I got 858.1. The unit will be centimeters squared because you have centimeters times centimeters gives us centimeters squared. And our last example, we have a subtraction in the numerator. We have a multiplication in the denominator. So we'll do each one separately because they're in brackets. So the top one, 74.335 minus 74.332. I got 0.003. It'll be meters. Again, we need 3 decimal places because there are 3 decimal places in the question. Each of the numbers. And on the bottom, when we multiply the two, you should have 3 significant figures. So when I multiply 4.75 times 1.114, I get 5.29 second squared. And now when I divide the top number by the bottom number, I should get 1 significant figure because the top number, the numerator, 0.003 is 1 significant figure. So when I do this calculation, I get 0.00056. However, we want 1 significant figure, so it's going to turn out to 0.0006, and the unit will be meters per second squared. These are some unit conversions which you will have to be familiar with. How to go from, for instance, centi to the SI unit. So let's say we had asked for centimeters into meters, centimeters into meters. We know century means 100, so there are 100 centimeters in a meter. Decade, there are 10 years in a decade, so the conversion is 10 to 1. Milli, 1,000. Micro, a million. so etc. So you have to be familiar with this metric system and how to convert from one to the other. The second topic is density, which you'll be doing in this lab. So density is a measure of the amount of mass within a given volume of substance. So it's a mass divided by volume. So we know this for water. The density of pure water is 1 gram per mil, or 1 gram per centimeter cubed. But you'll be working with finding the density of a solid object, of a liquid as well in this lab. So here's a typical question. Bowling ball has 340 centimeters cubed. That's the volume. The mass is 8 kilograms. Always pay attention to the units. How would we find the density? It would be mass divided by volume. So we get 8 kilograms divided by 340 centimeters squared. If we want the answer to the correct significant figures, in the question we have 2 significant figures for the volume. We have 2 significant figures for the mass, so your answer needs to have 2 significant figures. As I just said, water has a density of 1 gram per centimeters squared. And here we have some examples of things that will float or things that will sink compared to the 1 gram per centimeter cubed. We know that density is an intensive property, which means that no matter how much substance you have, it will always stay the same. So if you have a bathtub full of water, if you have a cup full of water, the density of that water is still going to be 1 gram per centimeter cubed. So that's an intensive property. So in this case, air has a lower density than water, so that's why air is above us. However, we have things like copper and gold, which have a higher density than water, so things will sink. You don't have to memorize any of the densities. You would be given, although you will have to know that the density of water is 1 gram per centimeter cubed. I would say that's the only one you have to know. So this just shows the copper sinks, the cork floats. So let's use this density equation to solve a couple of problems here. You can pause the video and try on your own. So we'll come back. This first question, we have what is the mass of the bar of aluminum having a volume of 2.0 liters. So the volume here is 2.0 liters. The density is 2.7. This is D. However, the units are in milliliters, so you have to convert this volume to milliliters. So this comes out to V equals to 2,000 milliliters. Remember, 1,000 milliliters in 1 liter. And you know D, so if we have D equals to mass over volume, if we want to find the mass, it's going to be mass equals to density times volume. So you're going to multiply 2,000 times 2.7 grams per mil, and we get 5,400 grams. And this is it's going to be 2 significant figures because in the question 2.0 liters is 2 significant figures. In the next one you have a beaker of water, which is 1 liter. And then you add, so this is going to be 1 liter. You add some metal in here into the water, and then you get a higher volume. So now you have 1.3 liters. So you want to find the volume of the metal. It's going to be 1.3 minus 1, which gives us 0.3 liters. So this is equal to V. And you also have the mass here is 11.3 grams. So M is equal to 11.3. So when you do 11.3 grams divided by 0.3 liters, again, these are the metal properties, you're going to get a density of 37.66. However, in the question, there's only one significant figure here in the denominator, so therefore your answer can come out to 40 grams per liter. So pay attention to the significant figures when you do lab number 1. In lab number 1, you're going to do something similar. You're going to find the density of a metal, where you put a metal into a graduated cylinder that has water. The water volume is going to change. You're going to have the mass of the metal, and you're going to use D equals M over V to find the density of the metal. In another experiment, you're going to graph different densities based on the concentration. So you have the concentration of sugar here. So hopefully when you do different concentrations of sugar, which are known numbers, you'll get a graph, and then you're going to find the density of an unknown. You can use the equation y equals mx plus b, which is the equation of a line. When you do get your unknown, you're not going to know the x value, which is sugar, but you will know its density. So you'll know the density, you'll know the slope of this line, you'll know the y-intercept, and hopefully you can manipulate the question to find out the percent sugar concentration of your unknown. So that's it for lab number 1. Good luck, everyone.